So in this talk, I'm going to talk about my recent work contributing to the KOKKOS package in LAMMPS. We don't have a lot of time for this one, but I want to emphasize that LAMMPS, it's very familiar for a lot of folks here, especially those from the KOKKOS team. For those who are not familiar with LAMMPS, it is a very big code base, mainly for classical MD tools to simulate a lot of systems ranging from the top to the bottom, from spin to molecular systems to in the macroscopic scales. And for LAMMPS, it is the prioritizations mainly for the spatial decompositions, where a big system being chopped into different bunch of boxes, the one on the top right, and for each subdomain is mapped to an MPI proc, and within this each MPI proc, we can have another degrees of parallelizations called X, and LAMMPS support different kind of hybrid parallelizations for multithreading, vectorizations, or GPU accelerations. So in a single executables, you can have mix or say different kind of accelerations. For example, OpenMP, GPU, and KOKKOS package built in. So we can switch just among those backends to use up the GPU if they are on the nodes. So in this talk, I mostly focus on one of the package that LAMMPS support, being the KOKKOS package. And as the names point out, this package powered by the KOKKOS library. And Christian and Stan are one of the earlier co-developers that bring into life of this package. And the optimal arrangement for KOKKOS to run is to have all the features in a single run ported onto the GPU. And so far, we have a lot of features within that run ported from the MPI version onto the GPU. And as I show in here, there's much more to come. And as early this year, we have mixed and single operations mode can be built within LAMMPS, which is very cool compared to other options. And then one of the good things is that now we can use all the ecosystems that provided by the KOKKOS to provide, to debug, and to benchmark this option for LAMMPS. You can check out the recent paper that the LAMMPS team put together. It is very nice about all the algorithm, all the improvement they have made up to this point. So what drives me to this work? So you can see the problem I want to solve here is try to make LAMMPS KOKKOS run faster and faster. And what you see in here, the plots showing how LAMMPS compare to HumDBlue, which is one of the fastest MD code that designed for GPUs from ground up. What I want to point out to you here is for these particular systems, for the range of the number of atoms, the one on the bottom, that show that if you go from left to right, you have bigger and bigger system size. And the fact is that HumDBlue is still something like around 2 times faster than LAMMPS KOKKOS. And the thing is that this is the most relevant system range where a lot of studies are conducted to gather statistics. And the community is saying that we are not going with LAMMPS KOKKOS until we match the performance gaps. And my interest here is that, is there any possibility at all to close the gaps? We try our best to close the gap for LAMMPS KOKKOS within that range of the number of the atoms in the system. So as usual, I use any kind of the thing in the toolbox to find what are the bottlenecks. Coming from my experience, I can know right away which would be the bottlenecks. But using the tools that provided by the KOKKOS lib, I can, let's say, figure out and pinpoint right away where are the kernels or where are the complete of all the slowness of LAMMPS KOKKOS. And then I can dig a little bit deeper to see what are the low-hanging fruit here. Can we change something or can fine-tune something within that functions? And it boils down to the team policies, let's say num teams, atoms per team, or the vector size. Essentially, let's say realistically set at the build time when we build the KOKKOS. And the KOKKOS package has been experimenting on different hardwares to choose what are the optimal, which is nice, which is very good already. But we're asking ourselves, is it possible to make it a little bit more flexible along the line? So the answer is yes. In this work, I expose all those parameters at different place in the MD run at different those and allowed users to specify or to scan over all the combinations that are available for the hardware. So the pull request is merged later last year, where we can run LAMMPS and specify all kind of those executions arguments like this. For example, the pair team size or the threads per atoms being 8 or 256. And what you can see here, this plot showing that if we just no tuning at all, we just switch to use the default version where you, let's say, chop the neighbor list of each atoms into a bunch of threads within the block. You'll see sometimes it's getting better at the low regions, let's say 28,000 or 56,000. But if you keep increasing the number of atoms, it's getting worse. And that's explained why people still, let's say, just use whatever the heuristic values are. But if we turn, let's say, if you scan over all the parameters, we can see that we can pick the better combinations to, let's say, close the gaps between LAMMPS KOKKOS and HUMDI Blue. And you can see that as early as 350K atoms, the difference between HUMDI and LAMMPS KOKKOS, it's very closer than before. There's some issues that we cannot match up the gap at the lower levels, at the lower atom counts. But I found the reason for this kind of thing, but maybe it's not really worth to push further to break a lot of things that it's already, let's say, better for the larger atom counts in this case. But the improvement is there, right? You can see without anything changed, without any optimization done, it's going from the orange to the dark blue. So that's mark what are the difference. This work contribute to LAMMPS KOKKOS package. And here's some characteristics that we can hope that where this work can contribute the most. For example, for the simple isotropic, the interaction between the atoms, then you can see the speed up, the last two columns showing that that's the default speed up without any optimization or any tuning at all. But if you go with the tuning to find the optimal set, you can see that it's boosts up to 5 times compared to 32 MPI ranks run for this particular system size. And if you jump up the workload that to be uploaded to the GPU, you can see the speed up even more significant, going from 6.6 times compared to 32 ranks to 12 times faster. So let's say double the speed up if you are having without the scanning over the parameters. And for the most challenging part is with the when we have the long range electrostatics, speed up, it's there. Not very remarkable, but something. And the work also applicable to other benchmark system as well. You can see the speed up compared to the non-optimizations around 60% let's say up to 40%. And only the chain system where we have very few neighbors per atom, then we don't see anything. So I also implement an autotuners, kind of similar to the way that Vivek just showed, but it's something like it's ongoing work. We need more time to work on this one. And there's a lot of things that I can tell you more, but the bottom line is that we can do much more work to, let's say, improve the KOKKOS package in LAMMPS. And I'm happy to open for any question that
Thank you,
have.
Trung. I think